Hi there, welcome to my videos on elementary differential equations. This is video number 11 for chapter 9 and the topic is partial differential equations. In the previous video we derived the D'Alembert solution for wave equation, so let's recall that. So this is the wave equation in 1D. And we are assigned with two initial conditions. At t equals 0, u is given as fx, and u sub t is given as g of x. Then the solution for this wave equation with these two initial conditions is the following. U of xt is half of f at x plus ct and f at x minus ct, and then plus 1 over 2c of this integral of the initial function g from x minus ct to x plus ct. Let's make some remarks on this form of the solution. So the solution is repeated here. So we see that as the way we wrote it, it consists of two parts. The first part here is caused by the initial deflection, so the initial shape of the wave. And so it depends only on the function f. And the second term here is caused by initial motion of the wave, where it's integrating the function g, which is the initial velocity. If we are considering the vibrating string problem, then the form here, the function f and the function g, needs to be extended. One needs to extend it into the odd function half-range expression onto the whole real line. So in this expression, doesn't look like it has two boundary conditions, and as t goes, and it will take value f from the whole real line. That's why this expansion is necessary. Finally, we comment that this solution is more general than the Fourier series solution. So in this solution, in fact, we actually have no requirement for the function f and g to be periodic. They can be any function defined on the whole real line. And this formula will give the solution for the wave equation. Okay, let's take an example by finding the D'Alembert solution for the wave equation. Here's a wave equation with c equal 1 and an initial condition, so the f is sine and then the u sub t, the g, is cosine. So here they happen to be periodic, but they don't have to be. Okay, so let's identify. So the f is just this one, and the g is just this one, and then c is 1. So this example is nothing but a practice of using the formula with these coefficients and functions given. Okay, so we know in the formula there is this integral of g. Let's work that out first. So we'll integrate from x minus t to x plus t of g of s. Putting in the expression for g, which is the cosine function with 1/5, let's put in the front. And then we know the antiderivative of cosine is just sine, and then the sine function is evaluated at x plus t, and then at the other end, x minus t with a minus sign in the front. We can now form the solution. And then the first part is half of the f function with the two wave speed, and then plus 1/10 of the part we computed as the integral of the g. Now let's manipulate this expression a little bit and try to find the forward-moving wave part and the backward-moving wave part. That is, I want to identify the two functions, the phi and the psi. Okay, so we can collect the terms, the functions that depends only on x plus t, which is this term and this term, we collect them together, and that's what we have. And then this term and this term, those two functions depend only on x minus t, and we collect them there. So we see that in the end, this thing is a function depending on x plus t, and this will be a function of x minus t. Okay, so let's call the function here to be phi of x plus t, and then this whole function here to be the psi of x minus t. Now let's try to identify these two functions. So the function phi here is this one, and it's a function of x plus t. So what will be phi of u, where u is just a general variable? Well, that is, you can just replace the x plus t to be your u. Okay, sorry, I actually should not use u. It conflicts with that. Okay, you can consider it to be y. And the function psi is this one, and it's a function of x minus t. And then if you want to call it psi of y, and then you just replace x minus t with the y, and you identify your function psi. Okay, so we see that in this solution, we can manipulate the terms and express it as two functions. One depends on x plus t, one depends on x minus t. Now let's make some further observation and introduce the concept of characteristics, which will be discussed further in the next video. We see that the solution of the wave equation can be written as the sum of two of them. Let's look at each term. What does it mean? For this function here, f of x plus ct, since it depends only on this quantity x plus ct, then along the lines where x plus ct equal constant, phi remains constant. So how does that look like? We can draw in the xt plane. So this is x and this is time t. So where is the line x plus ct? Equal to constant. So let me draw this with the green lines. So we see that these will be the lines that has negative slope. Sorry, pretending these are straight lines. And the negative slope is negative 1 over c in this plane. And similarly, the psi function depends on only x minus ct, will remain constant along lines of x minus ct equal constant. So if I draw those, so just draw, this is x and this is t, and then x minus ct is constant, will be on straight lines with the slope is 1 over c. So what it says is that solution psi is constant along that. And we know that psi depends only on the initial condition, some forms of f and g. So it will take some initial condition at t equals 0 and propagate that information into the region where t is bigger than 0. And so these lines where portions of the solution remain constant, so we can draw the other characteristics in blue. They will be going in that way. Right? Yeah, so these are special lines, and they're called the characteristics. Okay, so let me put them in words. So in the tx plane, and where you draw x as the horizontal one and then t is the vertical axis, then x plus ct constant are straight lines with slope negative 1 over c. X minus ct equal constant are straight lines with slope 1 over c. So these lines are paths where information is being carried along, and they are called the characteristics of this equation. So just a few very general remarks on characteristics. So this is actually a more general properties for many partial differential equations, even including some nonlinear PDEs. And then in general, these characteristic lines might not be parallel to each other as this case is showing, or they might not even be straight lines, and then the situation can get very complicated. Okay, so in the last video we'll talk a little bit more about characteristics, but restricted to the linear PDE setting. Okay, so that's all for this video, and I hope you enjoyed it, and I'll see you next time.